sure you remember that we asked you to look at some problems before this program, and here they are. What's the value of sine 0.5, and what's the value of that integral? And I've drawn the triangle here because a way of doing the first one might be to draw an accurate triangle, measure the sides, and so end up with the sine of 0.5. This angle is 0.5 radians. And the integral, well, I suppose the first thing that comes to mind is integration by parts, except it doesn't work because you end up with an integral that's worse than the one you started with. No, the way to do it is to use the third result that we asked you to look at, and that was the formula for sine. And once you've got the formula for sine, then it's fairly easy to do those previous problems. For example, you want sine 0.5? OK, well, you put in x is 0.5, and that gives you a first approximation to sine 0.5. If you want it more accurately, take 0.5 cubed over 3 factorial away. If you want it more accurately still, take the next term, and so on. And so you could get sine of 0.5 as accurately as you please. And the same sort of method will work for the integral that we had at the top here, this one. OK, now, in fact, what you're really doing is this. You're taking polynomials to start with the polynomial x as an approximation for sine x, and then taking a better approximation, x minus x cubed over 3 factorial, and then a better approximation, x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on. And those polynomials are called the Taylor polynomials. Well, the Taylor polynomials are polynomials which approximate sine, but it's a bit difficult to understand how a function like sine, which looks like this, which is awfully wiggly, can be approximated by polynomials, which are nowhere near as wiggly as that. So how is it possible, then, for a wiggly function like sine to be approximated by polynomials?
I can show you what Taylor approximations to sine actually look like. And I'm going to use some computer graphics that we've had drawn up. The first Taylor approximation is x, which is the first term of this formula. Now, the graph of x is this straight line. Well, the graph of x doesn't look very close to the graph of the sine function. Well, at least, though, they go through this point, the origin, and at that point, the two curves have the same slope. But what happens when we add negative x cubed over factorial 3? What happens when we add x to the fifth over factorial 5, and so on? What about the higher degree Taylor polynomials? Well, that's where the computer graphics come in. Well, that's sine x. And the first Taylor polynomial is just x. Now, to get the next polynomial, we add the term negative x cubed over 3 factorial. And adding these gives us a cubic polynomial. So we have the first two Taylor polynomials, and the cubic is better. At least, compared with the sine, it turns in the right places. Not only does it touch at the origin, but it's quite a good fit around that region, too. Now, the next approximation comes from adding x to the fifth over 5 factorial. In this way, we get the Taylor polynomials of degree 5. And this does even better than the cubic. At least it's a good fit near the origin and up to the first turning point. Now here's what the computer animation showed us. We had the graph of the third degree Taylor polynomial, and we had the term x to the fifth over factorial 5, which we added to it. Now, what effect does this addition have? Well, in this region, the values of x to the fifth over factorial 5 are very small, and so there's very little effect. But we have two other values for x to the fifth over factorial 5. Now, when we add those to the third degree Taylor polynomial, we get these 2 points. Now, those 2 points, the curve's now going to go through those 2 points, and so it's going to bend this curve up into this region. Now over here, we have negative values for x to the fifth over factorial 5. And so those values, when added to the third degree Taylor polynomial, are going to bring this curve down into this region. And so what we end up with is this fifth degree Taylor polynomial. Now, of course, that should give us a better approximation to the sign. Notice that in this region, we still have a very good fit, but we have a better approximation over here at this peak. Of course, as we go further along, we get a poor approximation. As a matter of fact, quite poor. But what happens with higher degree Taylor polynomials? The next approximation is built by adding negative x to the seventh over 7 factorial. How is this term going to change things? We'll watch and see. In fact, the two polynomials are certainly very close out as far as the first turning points. But how do they compare with a sine curve? Both approximations are quite good between the turning points. But this new 7th degree polynomial is a good approximation to sine for almost a whole cycle. But it's difficult to see just how good an approximation it is. But we can get the computer to calculate for us the difference between the polynomial and the sine curve at any point. Here at the origin, the difference is 0. Now, see how it changes as we move away from the origin. Between these dotted lines, the 7th degree polynomial is accurate to 3 decimal places. Here it's 2 decimal places. Here it's only 1. In fact, it's not until the difference is about 1 decimal place that the eye can see where the curves separate on the computer plot. Well, that's the polynomial of degree 7. We'll look at higher degree polynomials, but this time a little experiment. Which ones will coincide with a sine curve out as far as 2 whole cycles in either direction? Ready? Polynomial degree 9. That won't make it. Don't forget, you're looking for a curve that will coincide with a sine curve all the way between the left-hand line and the right-hand line. Degree 11. Degree 13. Degree 15. Degree 17. Well, the 15th degree Taylor polynomial almost made it, but actually it was an error at the ends by 1/10. It would take the 17th degree Taylor polynomial to give us the 1 decimal place accuracy. Let me summarize what we've done. Over here we have graphs of the Taylor polynomials for the sine of x. Now these pictures show us 2 things. First of all, notice that as the degree of the Taylor polynomial increases, the graph becomes a better approximation to the sine curve. Now the other point that these pictures show is indicated by the shaded region. Now what we've done is computed the region over which we have 3 decimal place accuracy for the Taylor polynomial. Now, notice that this region increases as the degree of the Taylor polynomial increases. And finally, that when we get down here to the 11th degree Taylor polynomial, we have 3 decimal place accuracy over a whole cycle. Now that's what we mean by a Taylor polynomial approximation to a function.
Well, I think it's about time we looked at where you actually got that formula for sine from. There's the formula. And you remember what you did? You assumed that sine could be written in that form, and you had the problem of finding the a's. And the first a naught, is easy to find because you get it by putting x equal to 0 on both sides, and out comes sine of 0 is a0. Then you differentiate. You differentiate this line so that, for example, a2x squared becomes 2a2x, and so on for the other terms. Then you put x equal to 0 again, and out comes cos of 0 is a1. And you do the same process again. You differentiate, put x equal to 0, and out comes the next coefficient. 2a2 is minus sine 0. And you keep on doing this. Differentiate again. You remember how you did this, and you got out the next coefficient. Minus cos 0 is 3 factorial a3. And now what you do is you put the a's back into this formula, and that gives you the appropriate formula for sine. But you know, everything that I've said there, although I've said it in terms of sine, could equally well have been said in terms of any arbitrary function. So for the rest of the program, we're going to talk about arbitrary functions, let's say f. Now, what effect would it have? Well, look up here. That would have become f of x. Sine x is now f of x. So that sine of 0 becomes f of 0. And when we differentiate, we get f dashed of 0. And differentiating again, f double dashed 0. And so on. Next one is f triple dashed 0. And then, when you do the same trick again, putting the a's back into this formula here, out comes this formula, general formula, for the Taylor polynomials for an arbitrary function f. Quite complicated looking, but once you get used to it, it's not too bad at all. There it is. Right, that's our general formula, but now we've got to decide what it means. Well, over here, I can show you that very well. So here's the formula again. And it really isn't too bad, because it's this term times 1 plus this term times x, this 1 times x squared over 2 factorial, this 1 times x squared over 3 factorial, and so on. So it's fairly easy to remember. But the interesting thing is that the derivatives are all worked out at x equals 0. And yet the Taylor polynomials can be worked out anywhere, so they sort of stretch out for all values of x. Now, I like to look at this as a sort of recipe. The ingredients are the 1x, x squared over 2 factorial, and so on. And the recipe is the values that you attach to these values of the derivative at the origin. Now, this is a good way of looking at it, and we've got this on a computer display for you, and it'll come up on the screen over here. But here are the ingredients. Here's the recipe. Suppose, for example, that you wanted to have f3 at 0 equal to 5. That would mean taking 5 lots of x cubed over 3 factorial. Well, this experiment builds up a particular Taylor polynomial, and it does it one term at a time. And on the screen here, there are the axes, and in the boxes here, we'll store the elements of our recipe. Well, we'll start with this first value set at 0, and then we'll increase it. See? It goes up. And now we can decrease it. Set it down. Now, these spaces here are kept for the zeros of the other derivatives. Everything else is 0 at this stage, you see. But now, if we leave this up at 1, then we can move on to the first derivative, which governs the slope at the origin. And, of course, that's independent of everything else as well. And we can start by increasing that. Up. And I think we'll bring it down again. And finally, I think we'll leave that one set at 1 as well, so it'll come round like that. There it is. So what have we got? 1, 1, and now the second derivative, which governs how much of x squared over 2 factorial we're taking. And of course, the space up here, this space, is the space that tells us how much of that we're taking. Now, let's mix it in and see what effect that has. We're mixing it in now. Now, of course, it's not going to affect the height or the slope at this point. So the flexing that you can see is entirely due to the changes in f double dash at the origin. And f double dash is the part of the recipe which controls the x squared over 2 ingredient. Well, for a change, we'll leave that set at -1 this time. Well, it's very easy to read off the recipe for this curve. It's just 1 lot of 1 plus 1 lot of x minus 1 lot of x squared over 2 factorial. Okay then, let's move on to some more derivatives. Let's first change the third derivative. Now the thing to notice is that although we're getting lots of curves by changing the amount of this ingredient, they all look alike near x equals 0 in the middle of the picture. Now we'll leave that value set at -1, the third derivative set at -1, which is -1 lot of x cubed over 3 factorial. And let's move on to the fourth derivative, and pay particular attention to this area in the middle of the screen. We'll leave this set at 1 this time.
The Taylor polynomial that Graham had was this one, with this derivative pattern. Now, what function was Graham aiming at? Well, there are lots of functions having this fourth degree Taylor polynomial and these 5 terms in the derivative pattern. One such function is sine x plus cosine x. Now, if you compute the derivatives of this function, and we're going to ask you to do that after the program, you'll notice that we get the derivative pattern 1, 1, negative 1, negative 1, 1, 1, negative 1, negative 1. And you'll also see that the fourth degree Taylor polynomial is a pretty good fit to the function, at least at the origin, where you'd expect. Now, we're going to set Graham to the task of matching these 3 derivatives, and let's see what the higher degree Taylor polynomials look like.
So we're aiming for the 5th, 6th, and 7th derivatives to be 1, -1, and -1. And we'll look at the effect of adding in each new term one at a time. And to help us to gauge their effect, we can ask for our target function sine plus cos to be displayed on the screen. See? Again, we'll start with the 5th derivative, set at 0, and increase it. That's too far. We'll leave it set at 1. Now set the 6th derivative to -1. That's too much again, I think. Right, that's the 6th degree polynomial. And finally, we'll adjust the 7th derivative to -1 as well.
You're probably a little suspicious of our good fortune. The functions we've chosen so far have been such that the Taylor polynomials have behaved exactly the way we wanted them to. They get closer and closer to our function. However, suppose we're not quite so lucky. To get an idea of the difficulties that can arise, let's consider this function, 1 over 1 plus x. Now, for this function, the Taylor polynomials do not get closer and closer to the function. We can show this by finding the recipe for the Taylor polynomials. Now, we've computed the derivatives, and you can check these after the program. And if we evaluate these at the point where x is equal to 0, we obtain 1, -1, 2 factorial, -3 factorial, 4 factorial, -5 factorial, 6 factorial, and -7 factorial. Now, look at this derivative pattern. We have 1, 2, 3, 4, 5, 6, 7 with factorials, and the signs alternate, minus and plus, after the first term. Now, let's give these values to Graham, and let's see what the Taylor polynomials look like.
Well, I don't love the way you said that. I think this is going to be a really tricky one. But here's the derivative pattern. There it is. And we'll take the terms one by one, and we'll see what that derivative pattern does to the Taylor polynomials. That's the first term. Now let's alter f dashed. That's f dashed, and now let's try the next term. That's the second degree Taylor polynomial, and we can leave it behind to compare it with the third degree Taylor polynomial. This polynomial is already a good approximation around x equals 0, but clearly it's not approximating any of the curve at the bottom left of the screen, and neither is it at the right of the screen. And the same is true for the fourth degree polynomial as well. So let's take a closer look where it does seem to fit. Here's the fifth degree polynomial. Now the polynomials wag up and down beyond x equals 1, so however many terms we take, the region of good approximation will never grow out beyond x equals 1. So we end on a note of warning. You can always calculate the recipe for the Taylor polynomials, but there's no guarantee that they're going to work for all values of x. But nevertheless, you know, the Taylor polynomials are one of the really big payoffs of the calculus, because with their help you can tackle problems which are otherwise well nigh impossible, as I'm sure you've discovered.